my presentation will make efficient addition to this line, and also hope you can find something useful in this work. My name is Shun-Peng Zhu from China. Actually, right now is already midnight here, so for this work also comes from cooperation with Italy colleague and also US colleague and also Portuguese colleagues. About me, also right now I'm working in University of Electronic Science and Technology of China. And right now, my research interests focus on the probabilistic physical failure modeling and uncertainty quantification, and also fatigue reliability design and life prediction. So today, my topic will focus on this line. And here about my university, also leading university in science engineering of China. Here are some views of my university. And also about my position also right now here, I'm located in the southwest of China in the Sichuan province at Chengdu city. And about the city, and also I want to just give a short introduction. And also, as we know, China is a panda of Holland of Panda. Actually, panda comes from Sichuan and Chengdu city. And for this, also in Chengdu city, we have a lot of beautiful things, beautiful food, and beautiful opera, and facing change, and beautiful tea, and delicious tea. And so these are the basic some information of my city. And I hope in the near future, if you have some chances to visit this city, and I hope you can enjoy, and also please let me know. So after the short introduction about me and my university, today my lecture will focus on the following contents. First part, I will give introduce on the background and motivation. And for this part, after this, I will give you a series and methods about this line, and also which comes from from my research group's work. And then with 3 case study, and from the easiest one to a complicated one, from musical and to engineering case, then we'll give my conclusion remarks. And about this topic, uncertainty, today actually this topic I will try to bridge the probabilistic fatigue design and the deterministic design. And for this part, actually, we need to consider or address the uncertainty or scatter or reliability in the structure integrity or fatigue failure analysis. And for this part, background, actually, we try to elaborate these factors or uncertainties during the fatigue design. Actually, many in the low cycle fatigue design and the life prediction. And also here we try to bridge the specimen to the component which we need to consider the notch effects. And also in reality, actually, from the design and to the manufacturer and to the component usage, actually, in the former stage of a product, actually a small variation or fluctuation, it will lead to a large scatter or dissipation on the performance. So this is also the kind of black swan issue. And for the uncertainty issue, actually, it also related with the mechanism behind this failure issue. Like with the increase of complexity, the uncertainty actually is also from low and to high content. And for this topic, actually, so as I mentioned, I try to locate the uncertainty or effect in design or under fatigue. So here is a slide about the failures. Actually, in the middle of this slide, actually is a kind of for a large amount of product. Actually, it has a failure curve or failure rate curve. And for this curve, actually, with a large amount, usually it shows a big difference or scatter from the performance, actually, which is mainly related with the stress, like from different customers, from the north, from the south, from different areas, different usage. And from the product itself, actually, it's mainly related with its strengths. This is a general concept for the inherent property of the product. Usually, we can say that, like, from the materials point of view, actually, it shows a big scatter on the material response. For this is S&N curve. And also from the component manufacturing technique point of view, also it shows with different manufacturing precision, different manufacturing technique, it also shows different performance and also the inherent properties. So with this, actually today my presentation will mainly focus on the stress and the strengths, and I try to quantify the uncertainty or variability in both sides and also for the fatigue design. And here I will just give you several concepts with the variability or uncertainty. And for the variability, actually, we can say example like this. For on the apple tree, every apple have a different mass. So this is different mass. It shows variability. But the uncertainty, we can understand it like the variety of the apple is unknown. So this is kind of improved or the concept from the variability. And for the material science or our area, like variability here, example like the fracture toughness of a material. Actually, this is a kind of variability. And for the uncertainty, it's more like the correct stress intensity factor solution. How to solve this factor acutely, and so this is also will lead to the uncertainty. And also here in the bottom of this slide list several typical sources of variability and uncertainty. And for the stress, like loadings, loads, and the customer usage and the environment, and also like including temperature loads. And for the strength variables, and also it relates from material, processing, manufacturing, and also environment. And for the uncertainty, actually here we list statistical uncertainty, like also with incomplete data, also under with a small sample size of data. So we need to make a conclusion. So at this time, it will lead to the statistical uncertainty. And also modeling error. And also right now for the crack, for the earlier, like Yoga mentioned, the fatigue crack loss modeling, there are lots of FCG models, but how we choose which one, it also will lead to different modeling predictions. And also the human, sorry, also about the human errors, also is a calculation errors and also the judgment errors. And here I organized or conclude a detailed table, which also list almost the sources for fatigue life dispersity. And from the types, like the first one is material properties, is more like from the inherent dispersion of materials fatigue properties, like fatigue strength, strength intensity factor, Young's modulus, and also the measurement uncertainties and the statics due to the insufficient database and the error in operation, and also the internal initial defect distribution, and the crack, and also crack in interferences and the difference in proceedings of parallel materials, and so on. And also for the geometry size effect, also like from the size effect, or also we name the scale effect and notch effect, which also leads to the stress concentration issues. And also these geometry factors also can be raised during under the different design margins. And the third type is manufacturing and the processing issues, like also like for the surfaces machining introduced by the dimensional dispersions, heat treatment, and the manufacturing process. and also manufacturing terrains. And for the load and environments is actually the outside factors, which are like the working conditions, operating environments, and the surface type, and also there are some other factors listed here. So these are almost the sources for the fatigue, life, dispersion, and listed here. And here is a slide for a general concept for the fatigue reliability design or analysis, which is like for the inputs and outputs. Usually, we want to build the relation or quantify the relation between the outputs and inputs. We call it model process. And for this inside, we can also here we can name it a black box, which we can model it from the data-based or failure mechanism-based. So this is just a general concept here with the inputs and outputs. And for this inputs also is we need to quantify the inputs like the deterministic part and also the uncertainty or variability or scatter associated with these inputs. So we call it uncertainty quantification. And with this input outputs, then we can have the performance prediction or evaluation or assessment. So this is from this line. And also with this desired performance, we can go back to design like to design for the to choose the limited stress and also the load conditions and also other factors. So during this procedure, also we have here sensitivity analysis. Since this concept also here in my later slides, I will have some case on this topic of sensitivity analysis, which is a process to quantify the ranking or the effect or the influences of or different factors on the purpose, like on the performance, on the design purpose, on the design points. So we call it sensitivity analysis. We can rank them. And for the uncertainty quantification, actually here we will try to quantify it from these three types. First, from material properties and the dimensions. Also, we can call it geometrical uncertainty, and also loads variation, loads fluctuation. So these are the general concept for this framework. Here I give you examples about the scatter or the variations of the material properties. Here we have two plots. First one is a cyclic stress strain response for the 950X steel, which is a car steel. And for this one here we have almost nearly 338 test samples here, and we can see the along the different strain ranges. It shows different stress response. Also, we can see here it shows a larger scatter. And for the life response here also we can see for a given strain amplitude or stress amplitude, we can see that it will lead to scattered life. Scattered life is that like for this level, it will be more than 10 times. And so these are just examples data sets we will use based on these data sets to elaborate our this framework about the fatigue reliability design and assessment. And also here I have another examples about the uncertainties in fatigue. Here is a P3C aircraft in US, and also we actually this project I was involved during my PhD study, and for this one, and also we measured the field test of nearly 40 aircrafts at 100% fatigue life expanded point about the energy, exhausted energy. Yes.
Samo napred, možete uvek, nije uopšte sporno. Jedino mi je kritično, recimo, jutro.
And about this scatter, we can see here. Actually, for the exhausted energy, it shows a scatter here. And also in the laboratory test, we tested this aluminum alloy, and also we used the strain energy, also acoustic emission monitoring, and we try to plot the energy, also light energy, total energy density exhausted during the cycle, cyclic loadings, and for the different life point here we can see. From the life nearly for this energy point, we can see that life almost from the nearly one cycle to 100%. So its life scatter is almost very large. So for this issue, we need to handle this issue carefully and during the design and the assessment. And about the mentioned background, actually right now in the current standards in engine, actually there are some. Here I list several of them. For the British standard 7910, and Euro Code 3, and the German FKM guideline, and also nuclear SME nuclear design code. And for this one, this list 3 also here I list 3 as the mentioned rules. I mentioned the rules for the examples. For the Euro code here, we choose different for the failure probability at 5 point with different safety factor. And also with changing. And for the RCB nuclear code, and also here we lower the life side with 20 safety factor, and also at the stress side we lower it by the 2 safe factor. And for this kind is a kind of like phenomena like empirical safe factor. And also here is a traditional approach with 0.1, 0.10 minus 3 points failure probability. And for these standards right now, they are lacking of the theoretical part about explain how to choose or how to bridge these probabilistic design factors and according to our different loading conditions, different usages, and so lack of accurate procedure for this design. And right now, almost the semi-probabilistic and also some partial safety factors were introduced by these standards. And here and about the mentioned issues here, so I here will give you some basic concepts between the deterministic design and or probabilistic design and fatigue. And for the deterministic, actually from the concept for point of view, like for a satellite, from the past or from the last measurements, the position we can estimate or we can predict is a future position with a reasonable accuracy. So this is we can call it a deterministic. And for the London point of view, actually for for this car, for a car example, from the past measurements and the future position of this car, maybe it can be described by the probability or statistical averages. It's a kind of distribution. And for the deterministic design, usually the mentioned safety factor here actually is given for the distance from the stress and the strain. Actually, the strains divided by the stress, we call it safety factor. We give a larger safety factor, so we will keep the product more safer. But about these issues, we need to think about how large for the safety factor would be better, and how much better, and at what cost we can have. So this is a kind of deterministic design. Also, we need to think about these issues. And for the probabilistic design, actually here, as I mentioned, and for the stress and the strain, actually here is not a deterministic point again. It's about the distribution. And for this distribution, actually, we can also first we have two issues. First one, also we need to quantify the distance between the mean value. The mean value actually which influences the output, the performance. Second point of view, we need to quantify the scatter of the stress and also scatter of the strength. Then we can evaluate or design the performance of the product of our purpose. And for this, here we have a concept of reliability. For the reliability here, actually, we can here which we can be the shadow of this collection under this curve, which means is -1 minus probability of stress larger than the strength, So this concept I will introduce several times later. And about these distributions, also we have several statistics like the mean, like normally we use the mean or expected value, which also calculates the central tendency of the data, the mean value. And also the variance, and the standard deviation, also the dispersion of the data, like the former slides, the scatter, which normally used. And the third one, commonly used one is the COV, coefficient of violation, COV, which characterizes the different dispersions by the standard deviation divided by the mean value. Also, we have other skinnies, quarters, and covalences. These are also I think we already have some basic theory on this concept. And also for the distributions of stress and strength, and also here we have some other concepts like CDF, cumulative distribution function, which is like the boundary, and also is a integration of the probability density of function, probability density function here. And for this one, it's just example with this uniform distributed. And also we can have some other like a normally distributed and a log normal distributed and Weibull distributed. And about the other like the probability, like for the variables or for the variable of our interest located in the interval of this probability, and also survival function and failure rate function. So I will just and also the mean and the expected values and the variances. And for this part, we just give you some basic concepts. So right now, my later slides will follow this line. First part, I will try to quantify the example for the fatigue assessment, like for the uncertainty. Fernando mentioned 3 types, and used for the fatigue reliability design and assessment. Then try to transfer the uncertainty or relations of materials to the structures, like to elaborate the stochastic stress and strain responses, and also try to elaborate the design curves under notch effect. And about this line about the stress and strength, and we need to choose the distributions. Try to best fit. Here we mentioned these 4 normal, log normal, and Gumbel and Weibull. For these samples, 18 samples maximum load. And normally we can try to judge which distribution is the best by this goodness of fit test. And for this case, the Gumbel and the log normal, it shows a better performance. And for this, for the mentioned uncertainty here. For this first case, actually, we try to locate the material reliability and the load fluctuation. and based on the Coffin-Manson-based Queen equation and the Lemberg-Osgood model parameters, and also using the Latin hypercube sampling, which is also a higher efficient sampling technique than the Monte Carlo sampling technique, or just as mentioned by Abilio in the earlier presentation. And then try to quantify the stress-strain response at the notch areas, and for the quantification of the kinetic Hadron model parameters, and also the stochastic finite element analysis. And try to the third step, try to quantify the life response at the notches. Here we choose the Fate-Source accretion, which is commonly used in the notch in the multi-axial fatigue analysis. Then we try to model for the damage, probabilistic model damage. And then we used this try to locate the code and or the procedure for the fatigue design. And here is the detailed procedure or steps. First one, we try to quantify the material reliability. Then with this, we include the load variation with this notch specimen. This is a half symmetry notch specimens here. And under the anexial loading, tensor loading, but for the notch part, actually the multi-axial stress states. And for this part, we try to transfer the material variation and load variation to the stress and the strain response variation, and then try to transfer this to the damage or to the damage parameter. Here we choose the Fate-Source equivalent shear strain parameter. Finally, we try to output the failure probability and the life. And here is just basic ideas of the Fate-Source accretion. And for this accretion is actually a normal stress collection based on the shear strain amplitude model, based model. The right part of this equation is similar to the Coffin-Manson equation, but this part is under the multi-axial loading condition. So this is a shear stress coefficient and also some other relative parameters. And also here we can simplify it for the unaxial reversed low cycle fatigue. And also this is this kind of simplified equation. And here the normal stress sensitivity parameters K, which is very important for this model implication. So I think here I will just ignore the details. More formal information you can find from the work of this list in the bottom of the slides. And for the model parameters here, also mentioned about this 3, 4, and 6, and this shear modulus, and also the Poisson ratio. And this is just a view on this accretion. Also, we can use other failure accretion, but here we will use this just for example. And for the data set mentioned before, it's about 16 batches, and for the same material SAE 950X steel. And for this one, here we choose this seven parameters, try to quantify the performance of this material. And also here we have some correlations inside. Later I will give you more details. And about the inputs with the stochastic, we choose which part. Actually, this part we need to clarify the correlation between these seven parameters, and also some earlier architecture test for some parameters like for the B and C. They are almost treated as a constant. And so here we choose this three as the stochastic inputs, and also the median variables like for the K prime, cyclic strain coefficient, yet stress, and also for the normal stress sensitivity parameter K. And also for the constant here, we chose these three. So these are the inputs for this analysis. And for this simulations with the input, we try to these are the outputs. And for this here, we try to quantify, well, try to model the scatter here. For the green dots are the real test specimens, and for the blue curves actually are the probabilistic or the stochastic cyclic curves by this Chaboshi model modeling outputs. Here is just a transfer from the material relation to the stress and strain response relation. Here we quantify it by the Chaboshi model here by the three parameters C1 to C3 C1 to C3. Here are the middle for the parameter distribution. So these are the main from the materials and to the stress and strain response or at the node. And here is a flow chart for this simulation. Actually, from the input sources variability from these parameters. And using the Latin hypercube sampling, here we generating 1,000 populations with loads and also with loads and for each cycle. And for each cycle, we with the one input material response and the load with 3D finite element analysis and output the FS finite source shear strain and also the estimated life and go on, and then output the stress strain response and also life response. So here is the correlation analysis for these 8 parameters. From this results, we can see some parameters are some like the positive and the negative correlation and a very strong positive correlation with these parameters. And here are the results. Here are the results for this specimen, notch specimen. We tried 3 stress levels. First one, like here, with for the load variation with 5%, and here with the output. The dots represent the output. And for this axis is the equivalent shear strain amplitude, which also shows here we can have the response distribution. And for this axis, we can have the life distribution. And here in this curves, the red curve is the median. Normally, this one is the median. Also, in the handbook, this is the 50% failure probability of the design curve. And here we choose the strain level for this analysis. And here we choose we list another with the same load with a larger load variation. Also, actually, we can note from the results that the strain amplitude, it also shows a larger scatter, and a life also larger distribution. And these are the two results. And here just a table list about the two materials here, one 950 X steel, another one at 550 degrees C, high temperature. Also, we tried 3 stress levels and about the strain median and the life median behavior. And about the fatigue reliability design, fatigue reliability assessment here mentioned about the stress and the strain, strains. And here is the first interferences mechanism of stress and strains for a given life point, or for a designed life point. We can try to locate the maximum designed stress. Like here, based on the failure probability, we can have this one, or we can have this one. We can have this failure probability. So this is the first mechanism. And for the second one is the load life. For the load life, actually, for a given loading cycles, we can estimate its failure probability according to the life distribution of this stress level. The third one is the strength and damage interferences. And for this point of view is a kind of the damage point of view. Damage is accumulated. And for this damage accumulated, we can model in this tendency and try to also quantify the failure threshold and also the design, the cumulative damage behavior, and to find the failure probability, or to design the life, design life. So here is just I will give you the three interferences mechanism for the fatigue reliability design or analysis. And for here, we use the normally distributed for this load or resistance or stress and strength resistance. And for this one, with the failure probability, we can have this calculations. Here, beta is a kind of reliability index, which can be quantified by the mean value and also standard deviation. And for this, for the first material, actually here, based on the load life or interferences, like here for the target failure probability with 7 multiplied by the 10 minus 5. And for this one, we can locate is design life at a different load variation, based on this mechanism. And here is for the final purpose. And for this part, actually, we try to we quantify the safety factor with the load relation and also the material relation. And for here, we choose the different load relation. And here we can compare that. We can note that for different safety factors, actually for the different, we can have the equivalent located the equal load relation. For the 55% normally at this 2.5 safety factor with the same material properties. And also note from this figure that results that at the higher stress amplitude, the safety factor will be smaller, or will be larger for the larger load relation. And also here we list this the median behavior, and also for this is for failure probability with 0.1 minus 10 minus 3. And for this, we quantify the safety factor and with the material properties and the load relations. This is another materials at a high temperature. Also, we can have the similar results here, and for the relations between safety factors and the uncertainty. So here about the theory and the methods part, and here I list three cases. First one is a numerical cases. First one is the stress and strain interferences. As I mentioned before, and for the stress and the strength, and during the implication, actually during the normal usage, it's changing. Both the stress changing and the strength changing, and so the behavior and also the performance. So we need to quantify it. And this is the first one. How to quantify it? Actually, we need to know, as I mentioned, the median behavior and also the scatter, and how to really get these distributions. For the stress is a kind of a normally concept, generalized concept. It can be temperature lows and also some other stress concept. And strength is more like an inherent behavior of the product. And for here, we can calculate the failure probability by this cross section, as mentioned. Here, just a very simple numerical example. And for the stress, actually here we give for this distribution with the normal distribution, normal variables here with for the stress, for the strength is 200 with the COV coefficient of variation is 0.1, and for For the stress, sigma is 100, and for the CLV 0.2, and we can have the standard deviation. And for the safety factor is 2, is 2. And for this deterministic design, what is the corresponding failure probability or the probabilistic design? And for this part, actually, we have this rules. This rules we can also we learn it from the basic probability theory. Here I will just give the results here. And for the here we have the z function can be the strength minus the stress. We can have the mean. We can, based on these rules, we can have the mean behavior and also the standard deviation behavior by this calculation. And about the corresponding relation with the probabilistic design, actually here we can have this for the z. It's actually we call it a limited state function in the structural reliability. And for this, for the z, normally it is less than 0. We call it failure. Actually, here we can have for this normal distribution. We need to quantify it to the standard normal distribution. We can have the z standard deviation. For this, we can have the z score with 3.54. It corresponds to the 2 multiplied 10 minus 4 failure probability. So this means for this case, safety factor 2 means this failure probability. And for the fatigue data here, normally what is the expected distribution of this fatigue lives? And here is a basic equation. Also, we can quantify the distribution of the parameters inside, also the load and the life, load life. Here is also similar examples for the input variable distributions and the output. And also here is the input variables, output variables, and also here is the distribution percentile with different life, with different for the life point. So these are the case 1 due to the time limit. So I think I will give faster for the last two cases. Actually, these 2 cases are the similar part from the mentioned theories and the methods part. So this part actually is a component level. And for this part also we choose this 7 parameters with different distributions and also the CLVs. And for the variations in the cyclic loads here for this turbine high pressure turbine disk, we have 3 working conditions. For these 3 working conditions, we have named it idle and cruise, and also maximum continue. And here is the high pressure turbine disk for this case. For this case, first also for the material parameters and the load relations, and for the FE modeling with troubleshoot modeling, and then output the stress strain response, the critical regions, and also the temperature, including the temperature loads. So these are the response at the different load conditions, the three, and these are the corresponding life at the 3 conditions, And for this load spectrum, actually these 3 loading conditions comes from an entire load spectrum. So we can estimate the usage life of this turbine disk. And also the estimated damage, we can calculate it by the minor theory. So these are the results for the high pressure turbine disk, And here is the design for the failure probability at different design life. And for different life, we can locate different failure probability. And here we use the 2 different interferences mechanism. Like first one is load life, and the dot one is the strength damage interferences. And we can normally choose the conservative ones as the design, as the basic, as the final results, Also, the right part is the sensitivity analysis of this these variables and how to link the different influences of these variables on the output. Here, the density and the rotation speed and the material properties are the top three. So these are the second case. More information that can be found from this from our recent works. For the third part, actually, is also is a turbine-related disk. Turbine-related disk. And for this part, actually, we also start from the test and also the simulation. Test here is actually an overspeed test, which kind of accelerated the live testing, which we normally test it at the higher stress and try to extrapolate it to the lower or to the normal use condition. This is just the overspeed testing, rotating test. Then, similarly, we tried two schemes. First one, probabilistic SN curves, just as mentioned by the last presentation by Aurelio. And also another one is the stochastic finite element analysis here, and try to locate the fatigue life distribution and the fatigue reliability analysis and the reliability sensitivity analysis. And these are just the details can be found from this work. Here is the over testing spindle and testing tester. And for this one also we tested at five load level, and we measured these two dimensions, D1 and D2, before and after experiment. Also, we analyze it by also from the FE simulation. Also, we compare the results here. And this after the final test, we occurred that the accumulated plastic deformation at the bottom of the turbine disk. And here just the similar results based on the formal mentioned skins. And here I will just give you the results. These are the material inputs, and these are the correlation analysis. And these are the similar procedures, but here we just have two skins. The first one is PSN, another one is stochastic finite element simulation. We have two. And for this two, also these are the flowchart. We try to locate the final purpose about the reliability, fatigue reliability, and fatigue life, and also for the sensitivity analysis. Here are the results. PSN first one by the PSN curved based scheme, and for this one we located by the from the according to the nuclear design criterion by the stress and strain, by the correction, by the strain, and like in this in the lower life stage, in the higher or in the lower stress stage, we located by the collection by the life, and here is the output of the life distribution. And here are the second scheme as I mentioned before, and also we run the different stress levels and obtain the distributions, and we try to obtain the normal working speed distributions. And also here are the fatigue reliability analysis for different skins and also for different interferences skins. And here the sensitivity analysis here, and also we results shows that for the SN curve, actually this SN, S is the rotating speed to the life cycles for the parameters A3 and the omega rotating speed, and also these are the critical. So these are the case 3. And ongoing also actually we based on the material reliability, load variation, also we include the geometrical uncertainty. Here we as indicated in this figure, this is three dimensions. We consider it from the design margins, and try to quantify the output, And for this part also we have the output of this designed life with different failure probability, and also about the sensitivity analysis. And for the results, it obviously shows that the dimensions, these three dimensions shows big shows big influences on the output. So this part of work is also ongoing. So finally, here are my conclusions. And for this part of work, for this part of lecture, actually try to bridge the relations between the probabilistic design and the deterministic design. And we used several sets of materials and also component test data, and try to elaborate the relations from materials to component. And also here we lectured framework for the design under uncertainty. And for this part, also we tried 3 interferences, or actually 2, But in the third case, actually we also tried the damage and strength interferences, 3 interferences. And so the last one is possible, is practical, and to extend this design or assessment procedure from specimen to the component level, And so that's all. And sorry for the time. I think it's already past my arranged time. So finally, and hope you can find some useful information from these slides. And also, I want to acknowledge from my also collaborations from Italy and the US, and also Portuguese. And also, thank you.